right, good morning. How you guys doing? Doing all right? Today we're going to finish talking about the carbonate system. I think we will, I don't know if we're going to revisit it directly, maybe to a small extent with relevance to how it impacts solubility of other stuff. A few lectures from now, but mostly this will kind of be it, and then we'll move on to kind of introduce metal-ligand chemistry. What are those about? Why do we care? And discuss some of that. Hopefully my voice is fine. Okay, so the carbonate system, we've talked about it a lot already by now. In the closed system, that's basically what we've considered up to today. Anytime we've looked at a system, we've kind of assumed, but not said outright, that the total amount of carbonate is going to be constant. It's just we have some amount of it, and so therefore when we draw one of these PC-pH diagrams, we have this asymptotic relationship wherever we have one species that is the predominant one, right? And it's going to total out at that total carbonate. Well, as soon as we open the system, then we have gas exchange, and that can then potentially change. So we're familiar with this section by now. It's just a graph from before. So what about when we can exchange with the atmosphere? Well, I think I mentioned last time, today our CO2 concentration in the atmosphere is about 420 ppm. That raises approximately 1.5 ppm each year. And one thing that's interesting to note about that is we can actually observe a slight difference in the northern hemisphere and the southern hemisphere because it takes some time for the emissions to balance. There's more people and more industry, more human activity emitting CO2 in the northern hemisphere, so the southern hemisphere actually lags behind by about 1 ppm, so about a year-ish. So if we were to measure that CO2 in the atmosphere, that's kind of where it's at the moment. Okay, so then Henry's law is the equilibrium principle that allows us to understand the gas exchange from a gas into a liquid. Now, there are other gas exchange laws. You might have heard of Raoult's law. This one is, I believe, for higher concentrations, or let's see. I think it's higher concentrations of the gas. Whereas, 420 ppm, that's 0.42%, right? That's not a lot compared to how much oxygen or nitrogen there would be. Okay, so this is. So there are probably a few ways to estimate it, but for CO2, Henry's law does just fine, and we can have a Henry's law constant of 10 to the minus 1.47 in units of moles per atmosphere, molars units per atmosphere at 25 Celsius. Okay, so with that, we can then correlate our carbonic acid that we talked about last time to the partial pressure of CO2. So when we know how much is in our atmosphere, and of course we could also generate a different atmosphere in a bottle, or maybe watering, dealing with a aquaculture system or something like that, where we might elevate CO2 to help the plants. That could of course change. Or maybe we want to calculate what life looks like on Mars or something. We could certainly manipulate the partial pressure of CO2 and therefore have a new understanding of what our carbonic acid would be. So then we can further recognize kind of in the same breath there, that the total carbonate is going to be coming essentially straight from this equation, right? Because we can say we can define the fraction that is carbonic acid as alpha 0 times the total carbonate. And so putting these two together, we can then get an equation that tells us something about our total carbonate given these constants, given the amount of pressure of CO2 in the atmosphere, or in a given atmosphere. And then, of course, pH will dictate what our alpha zero value is, and also the Ka for carbonic acid. So the alpha fractions are going to, of course, they could have some temperature dependence, but under standard conditions, we're going to just simply know at a given pH what that alpha zero is, right? Because we've looked at this, we've seen that this is going to bring in that pH and Ka. Okay, so with all this together, it becomes quite convenient because then we can know something about the partial pressure if we're at equilibrium and we have some solution that we know about, or if we have equilibrium and we have some atmosphere that we know about, we can know something about the total carbonate in our system. Okay, so this is all in contrast with a closed system where we kind of assume it's closed off from an atmosphere. It's as if we had a completely full bottle and it's sealed, right? So the closed system assumes no impact of gas exchange, whereas our open system allows for that. So we could rewrite the same equation, put it in forms of CT, or put it in forms of the partial pressure there. Either way we go, we get some added tools for understanding and characterizing the system. This also means that some of the mass balance equations that we had previously used will no longer be necessarily correct. If we're looking at this total carbon is this, that, and the other, well, we've changed something in the system, well, then that total carbon might change, and that could throw a wrench in our previous assumptions. So in practice, what this would look like if we were to plot it on our log C versus pH diagram here, we can see a total carbonate line here that starts off, if we have acidic conditions, it's going to start off at a spot that is basically that's at equilibrium given some partial pressure in the atmosphere. So this value is just going to be driven by how much we have in the atmosphere and our Henry's law constant. But as soon as we start getting an appreciable amount of bicarbonate and carbonate, well, we're still going to have the carbonic acid itself will continue at equilibrium across this line, but it's not very favorable to have it in that form at high pHs. So a lot of this will then convert into the other species. So while we'll continuously have some carbonic acid added, the total carbonate is increasing because some of it's transferring over to these other species, is kind of the way to think about it. So the total will increase, and that's going to be pulling essentially the CO2 out of the atmosphere into the solution in that regard. We could also look at it going the other way and driving CO2 out of solution as we make it more acidic. Well, and really we're making it into the gas form, right? Now, if we increase the pressure, let's think of a soda bottle for a moment. We have acidified it and put a lot of CO2 in there. So those two things combined make it so that all that carbonate is in a phase that is ready to leave as gas. But then we've pressurized the system so that it's pushing more of that CO2 into the water, into the liquid. So if you were to neutralize the acid, then you're going to have a lot of carbonate in there. It's not necessarily going to fizz and come out until you acidify it again. Or if you release the pressure and you give all that liquid a chance to off gas, then you'll have bubbles coming out, right? And then the challenge for a soda bottle is to make sure that you're doing that in a way where it's coming out kind of slowly and not all at once, right? So if you do it all at once, you get a small explosion. Okay, so that's it's kind of ways to be thinking about this carbonate system. Now, if we want to go into it a little more in depth, I don't think I included this piece here. But in a closed system, we have essentially kind of three factors that we can do some sort of a factor analysis. And I'm just going to kind of give you a quick picture and gloss over it. The book has some discussion about it if we decide that we want to, if you wanted to go further. I think it was called it a factor analysis. So closed systems, we have a set number of variables that we might want to understand about the system. And if we change, let's say, pH, then it's going to shift something else. And there's that direct change. So there's, let's see, how do I say it? There's, I think, 3 variables we could consider if we're talking about pH, carbonate, and alkalinity. So other things that might be affecting that. So I'm going to say for the carbonate alkalinity system, there's kind of 3 variables. And if you know 2, then you know the other. Well, in the open system, it gets a little more complicated because we have the partial pressure of CO2. Let me also write. So in the closed system, if we know 2 of the pieces, we can find the third. In the open system, we have 4 variables. And so it changes things up a little bit. But given the relationship between the partial pressure of CO2 and the dissolved CO2, if we know 2, then I think we could still compute, let's see, how did it? It's going to work a little differently in terms of what we need to fully characterize the system. Trying to remember. Okay, I'm not coming to it right now, but I may come back to this. But the deal is that process of coming to find the pieces, as you can intuit, just looking at this graph, it changes things up a little bit, right? And you know, I intentionally kind of decided not to go into that, and then I decided to talk about it just now in person. But you can kind of get the picture of how that's affecting. It's a slightly different approach that we'll need to take. But overall, it's the same principles of equilibrium. Okay, so maybe I'll pull the book up towards the end. But okay, so we know that for these systems, we can write our alpha equations and solve for each piece, the bicarbonate and the carbonate. We can then also put alkalinity, the alkalinity equation, in terms of the partial pressure of CO2. And this is, you know, coming back off that topic a moment ago, connecting the different factors that we know about. If we piece them together correctly, we can get a lot of good information. So given that alkalinity itself, we would define, you know, typically as the bicarbonate HCO3 minus plus 2 times the carbonate plus OH minus minus H plus because we can write that, and because we can put each of the species in terms of the partial pressure, then we can know, or we can put alkalinity in terms of the partial pressure, right? So we can, if we've derived the partial pressure versions of bicarbonate and carbonate, then we substitute those in and have an expression for alkalinity that has to do with the partial pressures, the pH, and the known K values, including the K for the Henry's law. Okay, so that ends up ultimately being fairly convenient to know something about alkalinity given a system that's open to the atmosphere. Of course, we also need to know about what our pH is and the partial pressure. Okay, I think that's about all I really wanted to say about the open system. I guess there's one little bit more. We can use titrations to figure out what is our alkalinity in this type of a system. I'm not going to go too far into that, but you can kind of see here's a pH versus our net strong base system, and I think in this case we would be we could look at the pH going from high to low. We might be adding acid here. This might be net strong acid. And we can classify how the system is changing based on, okay, this portion should be alkalinity coming from the CO3 2-, and then we're getting the alkalinity from the bicarbonate, from just the OH-, and then at some point we're just looking at the acidity from H+. So we can go through that whole system, not planning to go into depth on that. We've taken a brief look at titration in general, so it's just saying that we can observe the same trends and the same distinctions, endpoints for a system where it's the carbonate that we're analyzing. Okay, the exchange of CO2 with water, it's actually a little bit slow if you have very still water. So if you very carefully open your can of soda and don't shake it, not offering much mixing, and then keep that very still condition, it'll actually take a while before all the off gases is the way to think about that, right? If you were put a stir bar in there and we're mixing it around, you were still careful with a pressure release, so it wasn't a fast pressure release, but you let it equilibrate, that gas will come off rather quickly. So if you, if it was good practice to bring drinks into the lab, you could test it, right? Drop a stir bar in there, which you never do for something you're going to drink, because who knows what's been on that stir bar. And then you could test and say, okay, one that's stirred, one that's not. You would probably see, 5 or 10 minutes, there'd probably be a pretty big difference. So the mixing or the gas exchange will be driven in part by that mixing of the two in order to bring it to equilibrium faster. One other note, you might have heard about total organic carbon as an analysis for water or wastewater. It's a thing we often use. We're going to oxidize all of the organic carbon in a system to become CO2 and then measure that. It's pretty useful. When you do that, you often need to first get rid of all the inorganic carbon because there's CO2 in the water as carbonate species that will come off and obfuscate your data unless you get rid of it first. And so almost any TOC instrument will have a purge step first where it's going to acidify your sample and then purge out all the CO2 that can then be released. It's probably using nitrogen or something like that to purge the gas out and replace any dissolved CO2 with dissolved nitrogen. And then that, you could measure it, and that would be your total inorganic carbon. You could also call it dissolved inorganic carbon. So if you've ever worked with that kind of thing, that's what you're doing up front. Now, sometimes what you're interested in is a TOC, so you don't really care about the tick, just the talk. But it's usually going to be there as some reference information. Okay, any questions, thoughts about the carbonate system? Feel all right about it? Okay. All right, so let's talk about metals and ligands. Overall, what I'm hoping we can learn is some general information about them, and then really about how and why they can stabilize metals in water. How they affect solubility, how and why is that important, and kind of what types of math or equilibrium equations do we need for such systems. Ultimately, this will inform treatment approaches if we want to get rid of metals from water, things like ion exchange or coagulation flocculation, and in doing so, typically precipitation, even water softening. A lot of these will relate to complexation in general. So a metal plus a ligand, that's a complexation reaction, and we can call even water in some sense a ligand if it's going to complex with water or with a metal. Okay, so that's kind of the big picture. So as I said, complexation, it's gonna be when you have a metal ion and other molecules come and attach themselves. Now, these are not typically described as covalent attachments. There is some history where we used to use that word. Covalent usually refers to very strong bonds. And in general chemistry, we would probably learn that as, oh, they are now have an electron pair that they're sharing and kind of a bridge. Technically speaking, if we really look at it from a physics standpoint, there's no real distinction between the different types of bonding. It's simply an interaction energy, and some of them are stronger, some of them are less strong. So depending on how you want to spin it, how you want to say it, you could call it what you want. But the convention nowadays is not to call this a covalent reaction or bond, rather a complexation. Now that in part means or implies to us, because we've decided to use that kind of language, that these are generally not as strong bonds. So they're prone to coming back apart. So they're going to be kind of equilibrium reactions in that sense, whether or not that metal is held by the ligands or not. And in the same way, by default, when we have a metal in water, it'll be hydrated by water molecules. And then when a ligand approaches, like a different one, there's going to be some equilibrium between releasing that water and replacing it with these ligands. Okay, so we can consider a metal ion in water as a Lewis acid, meaning that it's happy to accept an electron pair, which kind of makes sense because whenever you look at the periodic table and you think about metal ions, we're thinking about positively charged species, right? And we'll have, if we could take a look at their oxidation states, they might have some varied ones. Iron, for example, you could have in 2+ or 3+, and so that's going to be happy to accept electrons. That's a Lewis acid in that sense. It's not necessarily the case that it's going to make everything more acidic directly, but it's that Lewis acid definition there. So then that means the ligands are generally electronegative, meaning they have a strong affinity to electrons, so they typically have a lot around them. Maybe they're negatively charged, maybe they're neutral, but they can then, when they find that metal, they can donate or share that electron pair, a lone electron pair. Okay, So then you form a complex, and just one example I found on the web here. You see the metal as written as M, and all these this wider structure around it with molecules bonding at different spots where there's an atom that is happy to share some electrons. Okay, so in this case we have four. Excuse me, these guys also. So we have six atoms that are bonding according to that diagram. Okay, so then the complex, we have a central atom, metal ion, and one or more ligands attaching to it. Typically, we're going to have more than one, usually, and in fact, often more than two. The typical range would be 2 to 8. And the number of ligands that can attach, that's what we would call the coordination number. So Cn here, this is the number of ligands with which the metal can form the bonds. This has a lot to do with the atom itself and the electronic properties. So the electron orbitals that the atom has, how many of them are available and happy to bond. So there's some inorganic chemistry there that deals with the electron orbitals that could dictate the typical coordination numbers. Okay, so I kind of alluded to this a minute ago, but metal ions, they don't actually ever exist freely as just some free-floating ion. They pretty much always will complex with water, if nothing else. So anytime you've got one floating around, and again, the concept of complexation is kind of funny because you might say the same thing for anything in water, but we often will say Cl- is free floating essentially, or sodium, Na+. But realistically, there is some association happening. It's just very weak, and it might be here and then gone. Metals, I suppose, are probably just a little stronger, and so that you'll have pretty often, you'll see things like, let's say, I think there was an example in the book, zinc with 4 waters and the net charge is 2+. Something like that, where it's a zinc water complex, and if you were to get the fancy instrumentation to observe the size of this zinc atom or estimate it in some way, you would actually observe the influence of that little water shell floating around with it. So in general, these metals, they're going to have a little more with them as they're floating around, whether it's water or something else. So typically, that's going to be 4 to 8 water molecules or ligand bonds, something like that. There are a couple situations where it might be a bit different, but that's typical. And if you think about the periodic table, we often think of a scale that we're going from, 0 to 4 to back to 0 in some sense, or to 8, right? So it's like the first 2 columns, you've got +1, then +2, potentially +3, some transitions, carbonate plus or -4, and then you're going to minus, right? So it's kind of that typical core shell electron business, but with larger atoms, sometimes that can be a little varied. Okay, so ligands then, we can classify them by how many bonding sites a particular molecule has. So water would always be monodentate, meaning it has one atom that it can use to share with, one atom that has an pair of electrons that can share with the metal. So bidentate then would mean it has 2 bonding sites. You could go to tridentate, tetradentate, anything, really we could say is multidentate, right? And if we look back at that little example image I had, this appears to me to be one molecule, and it's sharing 6 atoms with that one metal. So that's definitely multidentate, and we could basically just say, okay, that's this this ligand is that of that type or of that nature. So another way we can describe ligands then is by what we call chelates. So chelating agents, and you may have heard of these before. Maybe if you're at the grocery store and looking at all the different nutrient supplements and things, you might see chelated iron or something like that. The Latin here for the word chelate comes from claw. And so you can just imagine it's something that's happy to grab the metal, right, and hold it, is kind of the idea. It probably has multiple prongs to do so. So we would define a chelate as any ligand that has two or more bonding sites and forms some sort of a ring type of structure around the metal. So like a claw. And that's, we're going to convey it that way or call it that way because in general these have a bit stronger affinity and they're more thermodynamically favorable and just form stronger bonds. So if you do consider, like nutrition for a relevant case example, some forms of iron or zinc or whatever, magnesium, may well be more or less bioavailable to us given the type of chemistry our bodies are ready to take up versus the type of chemistry that happens to be, that the metal happens to be in. So it's not all just silliness to, think, okay, well, iron is iron. Why do I need this chelated iron or whatever? It also might be kind of silly to think that we can get all our iron from broccoli because it could be chelated in the wrong manner, right? And chelated was in such a way that's not bioavailable. So if we want something that is bioavailable, well, one thing to consider is that animals that are of similar makeup, if they have iron in their tissues, then that iron is probably going to be pretty bioavailable to us, right? So there's a potential difference there in bioavailability from plant versus animal sources of food. There's also consideration there, certain types of chemicals in, let's say if you had a lot of spinach at the same time as a lot of nice bioavailable iron. If it's the case that that spinach is chelating it and tends to do so to make it less bioavailable, then you wouldn't want to eat those two sources together, actually, because then it's going to chelate all the nice bioavailable iron and prevent you from getting it and obtaining it and pulling it into your body like you want it. Now, I don't know to what extent that it's all relevant to us or whatever. Chances are a good diverse diet is going to be a good thing, and we're not so desperate for it, that one molecule of zinc or iron, but might be something to explore if you had some sort of deficiency or something. Because I think that type of chemistry is important, and we could also consider that our stomach generally should be acidic, and that acidity, as we'll see as we continue with some of this, is likely very important to exactly that type of process relevant to our own human bodies. Okay, so we can take a look at a few different chelates or non-chelates here. So here we have zinc with amine groups or ammonia chelating it. So we've got a zinc +2 with 4 NH3 groups that are chelated, they're not chelating. So these would be complexing it. So we have a complex here, but we don't have the ring structure, right? So we're not going to call that a chelate. Here we have zinc with a water, another water, and then here we have this molecule that is chelating it because we're kind of forming a ring, and we have two atoms on that are on it. And we could continue and look at C and D here to see, okay, here's Here's another one. It's got 4, and this one also with 4. So let's see. Yeah. Okay, cut off what D is, but it's just naming the different pieces there. So we can see it, we can imagine that there's quite many agents that can do this. And some of them are going to be going to stick to it a lot stronger than others, is kind of the point. Okay, some other considerations for when and why complexation might be important. I kind of gave an example of what I think may be relevant for our own lives as humans eating stuff. But in general, chemical systems, ecological systems, there's quite a lot of cases where this stuff's important. So a couple of examples and more notes on what's going on with the metals. Well, sometimes the net charge of a metal could be changed. Now, I say net charge, we're not adding or subtracting charge to the total system, but if we had this atom, this metal atom, and we're thinking of it as a unit, and suddenly now we're chelating it or we're complexing it, and the complexing agents had a lot of negative charges, then some of these will satisfy the positive charge and could even then confer a net negative charge on this complex, right? So if we had a +2 metal and we complex it with 4 - 1 ligands, then we end up with a -2 total complex, right? So just sticking them on there, we might end up with a totally different acting chemical in the water. So an example one of the books provides is gold in seawater. So if you didn't know, there is a little bit of gold in seawater. But if you're thinking about, okay, how am I going to extract this and harness it and make myself rich? Well, you actually need to look at an anion exchange system, because chlorine is or chloride is going to be the chelating agent. And so you'll have AuCl2 with a 1- charge, or AuCl4 with a 1- charge for the gold 1 and 3 oxidation states. So we'll talk a lot more about oxidation states and things like that, especially as we get to the redox chemistry. But just a quick little reminder, many of the metals, transition metals, can have multiple oxidation states that they're kind of happy to be in, and can be changed from one to the other. So gold very often is in the 0 state, but you can get a little bit of it into the 1 or 3 state. So that's pretty neat, and there's a lot of ocean water out there, so you could potentially extract gold from the ocean, but we have to keep in mind there's only about 0.4 nanograms per liter of those species in typical seawater, or 10 to the minus 11.7 moles per liter. So that's a lot of liters to get 1 mole of gold. Of course, 1 mole of gold would be quite valuable if you could grab that. Okay. So complexation then, with all this in mind, it could potentially increase the total metal in solution. That's actually generally true. That will enhance its ability to be transported in the environment. If you stop and think about it for a moment, a metal that a lot of times you'll have some metal as part of a clay mineral or some other mineral material, and the solubility itself might not be that great. In fact, a lot of times you'll have some relatively insoluble mineral. Well, as soon as you do dissolve a little bit of it, which generally, if we think back on our equilibrium chemistry, generally there's always going to be a tiny bit that will dissolve. Even if it's very unlikely, there will be a very, very tiny amount that dissolves. But as soon as that happens, if there are chelating agents around, then suddenly you could make it more stable in solution. And so you are then, like if we think back on our discussion of, it's really, really hard to have a very pure substance, because if you drop that activity really, really low, then it kind of pushes at least just a tiny bit across the threshold. Well, the same thing could be happening, and then you're removing, let's say, iron in this case for the humic substances. The humic substances, they're like soil organics. Soil, maybe plant materials, stuff like that. So as soon as those act to complex Fe3+, which is normally not very soluble, well then we've reduced the effective concentration of iron back closer to zero again. So then it promotes a little bit more coming off. So that type of process can be, in a way, stabilizing metals and promoting a little bit more to come off. Of course, that's going to be kind of slow. It's not like it's going to leach it all off really quickly or anything like that. There's a potential risk there. So the bioavailability might be a good thing, but it also could be increasing exposure to toxic things, maybe arsenic, for example, right? If you have ligands that are stabilizing arsenic, that's not so good. So it's a pros and cons here. Talked about the bioavailability for our own bodies, also true for other living organisms, and could change, improve, or decrease the bioavailability of certain things. So that might be promoting growth if something was limited by some sort of a micronutrient, or potentially a bad thing with toxic effects. In reverse, we might reduce the amount around in some cases and thereby reduce toxicity. So aluminum is a good example. Aluminum is quite common in the environment, but aluminum 3+ is toxic to fish. So aluminum hydroxide, AlOH3, it's quite insoluble at neutral pHs, which is very convenient for us, especially when we do coagulation. So we'll add a bunch of Al3+, and then adjust the pH and cause all this to precipitate, and it's going to remove that aluminum out of solution, and that would be protective for anything that would find it toxic. Another example using aluminum is at lower pHs, aluminum will complex with fluoride, and so AlF2+ and AlF2 single plus don't happen to be so toxic. Probably the reactivity is a little lower since the AlF is probably pretty inert, I would imagine. So those will form at low pHs, and then you won't have so much toxicity at that point. So that's just a glimpse. There are quite a lot of scenarios where we might have more or less toxicity, more or less solubility, things like that. So hopefully that's a nice impression of when and where it might matter. Okay, so another way to think about ligands and to kind of understand different properties of them would be to describe them as either inner sphere complexes or outer sphere complexes. We're going to start with inner, and most of the complexation, most of ligand chemistry, we would call the inner sphere to be the true complexes. And really what that's referring to is there's a direct replacement of the water molecules and therefore a direct bonding between the metal and the ligand. So we'll say direct metal to ligand bonding. As we'll see, that's in contrast with the open. So the ligand then is replacing the water, and then you have direct overlap with the ligand's electron orbitals and the metal's electron orbitals. That, in fact, I mentioned this earlier, that's the very definition of any kind of bonding, is overlap between the electron orbitals providing some interaction field that's attractive, essentially. So then the coordination number, Cn, that's going to depend on the availability of these SPD orbitals. If you recall from our from kind of general chemistry, different atoms have different orbitals. They're going to be shaped differently, and if you have a large, complex, heavy atom, you're going to have many of them because there's lots of orbitals. But S is typically the outermost one, and then followed by P, then D. So the inner ones are not usually interacting so much with the stuff outside, is probably the way to think about that. So occasionally we'll have something crazy like uranium 4 here that can have 12 ligands complex it, or 12 attachment sites essentially. Sometimes you'll get an odd number, but almost always it's an even number of ligands that you're dealing with. And that just kind of has to do with the nature of these orbitals. Typically are, would be kind of in even numbers for the system. Okay. How does it look when we complex them? Well, we can have a few different structures. Having a coordination number of 2 is pretty rare. There are a couple examples. Silver and gold, we already kind of mentioned, they're pretty rare, especially in fresh water, but they can make 2 coordinated systems. I think we said AU with CL. If we do 2 CLs like that, it would be a linear molecule. One of the books also talks about the extremely toxic dimethylmercury would also be linear, but that's maybe an organometallic, not a complex. So there's some distinction there that maybe has to do with how strongly bonded they are. But if you did have this guy, if you haven't read about it or heard about it, there's a terrifying horror story of a researcher that was working with that. Good case example to reminder to be safe in labs. This stuff, it's incredibly toxic for a few reasons. One, mercury is bad, but primarily it's very, very bioavailable. So it's going to, as soon as your body encounters it, it's going to be taken up and brought to your brain rather quickly and have a lot more activity than just mercury complexed with water or whatever else. So it's extraordinarily high in terms of its impact on a biological system, and it passes straight through your skin and straight through most lab gloves. So unless you're working with the correct laboratory gloves, or if you even if you are wearing the right ones, I think the story goes that the researcher, she had a drop spill on her arm or something and didn't know it. Weeks later, she started having seizures and showing symptoms. And they traced it back to an exposure sometime previously. Mercury is no joke when it's a bad case of it. So probably as soon as she had that exposure, she was doomed. I don't know if they could have done anything. Maybe if she'd noticed it right then, perhaps some sort of treatment. But as soon as it was in her brain, she didn't have much more time to live. So that stuff's nasty. Never work with it, and tell all your friends not to. Okay. Anyhow, we can kind of see that based on what's going on here, it can have an impact on how it's showing up in the environment, how it's interacting with other stuff. Coordination number 4 is pretty common, and that's going to show up as a tetrahedral or a square planar. So it could be either of these forms here. A coordination number of 6 is going to give us an octahedral situation. It sounds like 6 should be, should not have 8, right? But octahedral meaning the 8 planes for the system. And if you have 4 corners like this and then a top and the bottom, that's giving you an octahedral shape. Okay. So, I think last thing I want to say about the inner versus outer shell stuff. So outer sphere complexes, they are different from the inner sphere in that they do not have that direct metal to ligand interaction. In fact, they don't even replace the water shell, the hydration around the metal. And instead, there's a longer distance interaction between the metal and the ligand. It's going to be an electrostatic interaction. So in that sense, it's no longer that more direct covalent-ish bonding where the electron orbitals are overlapping. We're too far apart from that. So it's just the electric field interaction pulling them together. So I guess when I said all bonds are the overlap, maybe I misspoke. This would be a weaker bond, but pulled together by the charge, right? Okay, so that part of the implications here would be that you can still have that interaction, but it's likely going to be a little weaker. You can't definitively say by measuring the bonding strength between these that it is an outer shell versus an inner shell. It's not, we don't have that much distinction between the bonding strength. There are some inner shell ligands that just don't bond very strongly, for example, and some of these outer shell ones might be a pretty strong distance. And if you think about the distance that a shell like this might have, this is probably on the scale of 0.5 to 2 nanometers, possibly even a little less. My guess would be this is like angstrom level, which is 1 angstrom is 0.1 nanometers. So kind of on the angstrom scale distance. I'm going to guess here and say 0.1 to 2 nanometers for a distance like that. So really, maybe I'm a little wrong. Maybe it's a few nanometers. That electrostatic interaction is going to be fairly strong, pulling it together, possibly to the point where you could get close to having that direct electron orbital overlap. Okay, so at any rate, there are ways we could estimate this bond strength. There's a Fuas equation. We could get into that. I don't think we will necessarily go there, but it's something that we can do. And I'm sure that if we looked closely, that's going to relate to the geometry and the electric fields at play. Okay, I think that's all I had prepared for today. It's been quite a busy one lately. So we will come back next time and dig a little deeper, probably a little more topic covering kind of stuff. What's going on with these? How do they work? Why do they work the way they do? And then start getting into some of the solubility implications is my plan. Okay, any questions, concerns? Okay, and I've not finished grading homeworks and things, but I'll try to have that. I will also upload grades to Moodle. You have your exams already, but I'll post the grades for you so you can kind of see that tracked in Moodle as well. So probably by next class period is when I'll get that stuff. All right. Have a good day, and I'll see you guys next time.